Hey everybody. Alright, we're continuing Chapter 3. We'll be finishing it up today. We have a little bit more to talk about in Chapter 3. So the first thing, where did we leave off? We left off at the end of the last lecture, kind of we figured out the selectivity of chlorination versus bromination versus fluorination for primary versus secondary versus tertiary. And the main conclusion here, remember, was that fluorination, for example, is very non-selective. It's like there's a tiny bit of preference or selectivity for secondary or tertiary, but there's very minimal. Chlorine's kind of in the middle of selectivity in terms of 1 to 4 to 5. So there's definitely a preference for tertiary. There's definitely a preference for tertiary, and secondary is also more preferred than primary, but there's not that much, And then we have bromination, which is primary is 1, secondary is 80, tertiary is 1700. So it's a huge preference for tertiary bromination. Okay, so that's kind of where we were. Let's try this in a problem. There's actually several problems on the website. It's on my public website. You should try. I'll just show kind of what they look like, I guess. I don't have my website, but it's handy. But it's going to be something like this. There's like 4 different problems, and you can try to step through them. That allows you to predict the halogenation major product of these 4 products. Okay. There's one up top also. So take a look at these. I'm not going to post the answer key yet, but I will in the next couple days. So you should try to do it completely from scratch. And if you can get the right answer, this will help you on the next quiz. Okay? All right. What's the magic word for these reactions? I think we decided it was going to be. Second. So the magic word for these kind of selectivity reactions, the selectivity reactions where we predict the products, the magic word we decided is going to be pickle. All right. So remember pickle for these selectivity type problems where we're predicting the selectivity of reactions. It's pickle. Okay. All right. Cool. So let's try one problem. I showed a problem down here. I'm not going to do this one. I'm going to do a different one to make it a little more fun. Let's try a different one. This one's one of the practice ones that I proposed for you guys to do, and you should try this one also. But let's try maybe a little more difficult one. All right. So. How about this one? Alright, so it's cyclohexane, so there's 6 carbons on the ring. 1, 2, 3, 4, 5, 6. And there's a 7th carbon, a methyl group there. And yeah, we'll get into the naming of these and all the properties next chapter, which is about cyclic alkanes. But for now, you know the basic idea, right? Alright, so let's do Br2. And what's the thing you also have to do for all these reactions? Either heat or light. Alright. You should be able to do, there's the mechanism also. There might be a mechanism type problem on the quiz. As a mechanism problem, it might be more like I'll do this as a potential mechanism problem. You might see this kind of thing on the quiz, and I'll just say heat or light. Okay, so this might be a style of mechanism problem that you might see on the quiz, where it's like, a pretty simple substrate, cyclohexane plus Br2, lighter heat, and then you get the bromide and the HBr. Remember, it's a four-step mechanism, so if I ask you this on the quiz, you're going to have to draw the four steps, and there's also magic words for the 4 steps. Okay. But anyway, we're not doing a mechanism problem here. We're just predicting what the different monobromination products are. And it's a different kind of problem, right? Predict unique monobromination products. Okay, and so how would we do that? Well, I first look at this, and I can at least count how many unique monobromination products there will be. I like to do it first by counting, and then I'll draw them. So I start up top, and I'm like, well, that CH3 could totally be brominated, right? So that's number 1. What's next? Maybe that one can be brominated, so that'll be number 2. And then it's like these guys are identical, like symmetrical, and so those could be the 3rd product. This could be the 4th product down here, right? That's a different monobromination product. And then this would be the 6th one, I think. Wait, 1, 2, 3, 4, 5. This is 5 total, I'm sorry. 5 total. So I see 1, 2, 3, 4, 5. So what I do then is I draw 5 copies of this. Actually, give myself a little more space. Don't squish it up too much. And I'll draw the 5th one down here. Okay, so I see 5 potential monobromination products. So now I'm going to draw the bromines at those different 5 places. One could be like up top. The next could be either on the left or right, or sorry, in the central carbon. Next is the central carbon, the tertiary position. Next I'll maybe put it here, and then next it'll be down here, and then next it'll be down here. Alright, cool. Alright, so we have 5 potential products, right? And they are all unique. None of these are the same. None of these are the same molecule. Now I give them letters. I'm going to say A, B, C, D, and E. Okay, we did the next part basically already in a different problem. We're going to do it again now. So I'm going to write A, B, C, oh god, over here. A, B, C, D, and E. These are the different products, right? A, B, C, D, and E. What we need to do is calculate which is the major one of these. Which is the major one? That's usually the goal, is to figure out which of these is going to be produced in the most quantity, and we can do that really easily, given our the probability that we determined for primary versus secondary versus tertiary bromination, right? So what was the first thing we did? We did this kind of problem last time. So I look at A, and what I do is I zoom in there and I see, well, that's that looks like it's a primary position, right? And also, how many different hydrogens in the starting material could be replaced to give me this product A? Well, how many hydrogens are there? 1, 2, or 3? It's 3, right? Yeah, so we write 3. 3 times something. We'll do the something later. B, how many hydrogens in the starting material would give me product B with the bromine right there? So I look there and I'm like, well, that's the carbon. How many hydrogens are right there? There's 1, right? So I say 1. Alright. C, how many hydrogens could I replace in the starting material that would give me rise to product C? Well, I look over there and I see, well, there's 2. However, remember there's 2 there and there's 2 there, and those make the same product. either all of those would make product C, right? Those two hydrogens or those two hydrogens, if you replace them with the bromines, would make product C. So it's actually 4 now. See how we got 4? Because we look there, we see all the Br can be put there, and then we look at the starting material and then we see 2 there, but there's also 2 there and it's symmetrical, right? So that's why there's 4. What about D? Well, there's 2, so that's where the Br is. Then we look over here, well there's 2 there, there's 2 there, so that's 4 also. Now we look at product E and we're like, well there's the Br. We have to move our pen way back over here and we're like, well how many hydrogens are on this carbon? Right? You look at that carbon, we're like, well that's this carbon. How many hydrogens are there? There are 2 there. Alright? So that's the first step, is figure out the number of hydrogens that could be replaced to put the BRs in the right places, right? Alright, so then what? Then we use our statistical probability of primary versus secondary versus tertiary. And this I always would give you, but it's the numbers for bromination on our little chart. Whoa. Remember, we're 1 to 80 to 1700. Primary, secondary, tertiary. 1 to 80 to 1700. So I'll just write that over here. It's 1 to 80 to 1700. 1 to 80 to 1700. Alright, so for molecule A, is this a primary or secondary or tertiary position? Right? Because there's only 1 carbon connected to it, so it's primary, right? I'm gonna rewrite this, sorry. Okay, it's 1 to 80 to 1700. Those are the 3 numbers we need. Alright. Okay, so for molecule A, that's the primary position, so it's a 1, essentially. For B, is this a primary, secondary, or tertiary position? B. Well, there's 3 carbons on it, so it's tertiary. And what's the selectivity for tertiary? 1700. And you can see now that we're going to have a big number right there, right? Now for compound C, how is it primary or secondary or tertiary? It looks like the carbon is connected to 2 other carbons, so it's 80. Okay, and then what about D is the same thing, because that's also secondary, 80. And then E is also secondary. You do the math, get a calculator out. 3, 1700, 4 times 80 is 320. 320 and 160, right? Now you sum them up. What's the summation of those? Get the calculator out. 3 times, 3 plus 1700 plus 320 plus 320 plus 160 is 2503. 2503. Okay? Now we figure out the percent of these. I'm just going to do, there's very clearly one product that's dominant. Product B is the winner, right? Just for time, I'm going to determine the percent of just product B. So it's 1700 divided by 2503. And that's 68%. So product B is produced in 68%. That's the prediction. All right? That's the kind of thing you will be doing on the quiz. You're also going to have to write our magic word, which we've said a few times now. The magic word for these selectivity reactions. All right? Alright, so we're still on number 7, which is selectivity of fluorination versus bromination. Versus bromination versus chlorination. As we understand now, fluorination is the least selective, and the bromination is the most selective, and then chlorination is kind of in the middle. Okay, and the question we're going to ask now is why is fluorination non-selective and bromination so selective? Alright, so fluorination is very non-selective. Remember the very low selectivity numbers for primary, secondary, tertiary. And this is kind of complex, but just, you know, understand that. I'm not going to ask you to explain this, so don't worry about doing this on a quiz or whatever. But it's still understandable. It's just a little, you know, there's a little bit of kind of theory here. Alright, so we're first going to talk about fluorination. Also, these are on a slide, so I'm going to show it, I'm going to draw it out, then I'm going to show you the slide. So, yeah. Alright, so fluorination is non-selective, we know that, right? It's very exothermic, we know that. We did the calculations, right? It's very, very exothermic. And we're also going to give it a word, early transition state. Early TS, early transition state. Alright, so alright, let's see here. Early transition state. TS is the energy barrier, the transition state. Okay, so the big thing that's going to explain this very non-selective fluorination is there's little differentiation between the primary and like secondary or tertiary reaction pathways. And this is how we can see this, alright? So as we go from, so this is going to be an energy diagram. We're going to draw a little energy diagram. If we go from like this, this substrate, and we imagine reacting with a fluorine atom, and so the fluorine atom can rip. This is the propagation one, prop 1. And there's energy going upward. Alright, so fluorine atom can either rip off the tertiary hydrogen or the primary hydrogen. And what we're going to see, so this is kind of like the beginning of the energy diagram. So it can either rip off one, and this is going to be the higher energy one, which is the primary. And then you form HF, right? It can either rip off the primary one, or it can rip off the tertiary one. If it rips off the tertiary one, you get a tertiary radical, right? Alright, so there's an interesting behavior here now, right? Because if the molecules can react versus one pathway or the other, is there a big difference in the activation energy, the EA, the little hump, these transition states, right? It does not look like there's a big difference. Very small difference, right? Very small difference. So is it going to really care which pathway it goes down? Well, there's not much of a difference, so it's going to be mostly non-selective, and it's either going to rip off the tertiary or the primary in very equal amounts to give rise to these products down here, right? Okay, and what the word we use to describe this, because essentially the structure of the transition state kind of resembles the starting material, and there's not very much difference between the pathways in the starting material. That's what we call an early transition state. Early transition state. So That's the word we use for this situation. Now I'm going to try to sneak in the bromination. Let's see how that, because that's the bromination is super selective, right? Energy is going up. And these are, propagation 1. All we're talking about right now is propagation 1, the first step, the first propagation step, propagation 1. All right, so there's a difference with bromination. So this is fluorination. This is bromination. All right. With bromination, it's actually an endothermic first step. All right, so if we have, whoops, sorry. All right. With bromination, we start with the substrate and Br dot, just like we did with fluorination. But it's actually, the first step is endothermic, and what happens then is we have two pathways. One that gives rise to the primary radical, the unhappy one, and one that gives rise to the tertiary radical. Because you can rip off either a primary H or the tertiary H. And as you jump up, you can go through one pathway or the other pathway, okay? And in the top one would give you the unstable one, less stable. We know primary is less stable. And the bottom would give you the more stable, HBr. Okay? We cool so far? Alright. So, and these are the transition states. Okay. Alright, so something different. In fluorination, the transition states were very similar. Bromination, the transition states are totally different. Totally different. And so there's a huge difference in the EAs. You can agree with me, right? Huge difference in the activation energies. And molecules really like to go through the lowest energy pathway, right? So if you're the molecule and you're the, if you're this 2-methyl propane and Br dot, which pathway do you want to take? The low energy pathway or the high energy pathway? You're probably going to want to go on down the low energy pathway, and that gives you the tertiary product, which we know is hugely selective. It's like 1,700 times more likely to go to give this pathway than this pathway, right? Isn't that crazy? Okay, so there's a word we're going to give for this, for bromination. We're going to call this is an early transition state. What's the opposite of early? Late. This is called a late transition state. Okay, and so essentially the takeaway here is that if you have a kind of an exothermic type of process, you always get an early transition state. And if you have if you have an exothermic process and two pathways, exothermic process and two pathways, the transition states will resemble the starting materials. And there's not much differentiation, right, between the two pathways if we look at the starting material. But the late transition state, when we have an endothermic process with two pathways, endothermic, now the transition states are deviating from each other, right? The transition states are deviating from each other, and they resemble the products. And the products are very different, because we know primary is not very happy, tertiary is happy. And what do we call that? Not an early transition state, but a late transition state. So that's kind of that's the theoretical rationale for why we get such a massive amount of tertiary bromination versus primary bromination. Why bromination is very selective and fluorination is very non-selective. Okay. Okay, this is from my slides for Chapter 3. All this is an exact replication of what I just drew. All right, and maybe a couple more words that might help you understand this. This is also figure 310 in the book, I guess. Figure 310. It's just showing the same exact thing. That if you do fluorination, there's two pathways with a very similar activation energy, and one gives you primary and one gives you tertiary, and with that very minimal difference, of course, there's not going to be much of a difference in selectivity, and that's what we see with fluorination. Okay, so then we have the other one, which is, I guess, figure 311 in the book, which is showing essentially what I just said, which is that when you have an endothermic step in a mechanism, endothermic, that gives rise to two different pathways. The transition states are actually very, very different, and then this explains why you get a large amount of tertiary bromination and maybe less primary bromination. Okay, so this is all in my slides. You can get this, put it in your notes if you want. I'm not going to test you on this concept. Okay, all right. All right, so let's see. We have one last little topic from this chapter, and this is also, we'll say, not quizable, so don't worry about learning about this. It just takes what we just talked about one step further and gives it a name. It's called Hammond's postulate. Hammond's postulate, and it explains it also explains the rate difference between like F2 and Br2, which we already know. Fluorination, non-selective; bromination, super selective; chlorination's kind of in the middle. All right, so it just says this in words. Thus, fluorination is exothermic, prop 1. Propagation step 1 is exothermic, yeah. And that leads to transition state 1 and transition state 2. To be the structure of the transition states, as we just saw, are structures. The transition state structures are, we call them starting material like, SM like. They resemble the starting material, okay? And little differentiation, we just saw that. Very little differentiation of the starting material structures, okay? Alright. Oh yeah, and what's the name? Is it early or late? We call it early. They're called early transition state. Okay. So that's, this person Hammond postulated this and wrote it out in words. So it's called early transition state, little differentiation, non-selective. Early transition states, in this case, are non-selective. Okay? And now we do bromination, which we just talked about. This is an endothermic prop 1 step. Propagation 1 step is endothermic. Now, transition states 1 and 2, the structure of the transition states, structures are not starting material like they were in fluorination. They are not starting material like, they're more product like. Product like, okay? And or in this case, you know, what's the product of propagation 1? It's the radicals, right? It's when I mean product, I don't mean the final product. I mean the product of that step, right? So the product of propagation 1 is either a primary radical, totally unhappy, or a tertiary radical, which is totally happy. Okay. And if the transition state structures resemble the product-like structures, or the product structures, these radical structures, that makes there a huge difference between the transition states. And huge energy difference in the transition states, right? And then we call the transition states late. Called late transition state. Late transition state, okay? And that explains, just in words, what we just showed in the figures, right? Early and late transition states. The fluorination one is an early transition state, little differentiation, and terrible selectivity. Bromination, you have tons of a difference between TS1 and TS2, the transition states. It's called a late transition state, and that explains the extreme selectivity of bromination. Alright everybody, we're done with chapter 3. On to chapter 4. Which are cycloalkanes. This chapter is not as intense with chemical reactions the way that chapter 3 was, but it has some interesting topics related to the structure of organic molecules. So cycloalkanes, as you probably can guess, is maybe alkanes that are cyclic. So let's show an example, a couple examples. In terms of simple naming, what do you think that might be called? It's 6 carbons, it's cyclic. It's not hexane, it's cyclohexane. Cyclohexane. Cyclopentane is 5 carbons. What do you think 4 is going to be? Cyclobutane. A little square. It's a little square. And what about 3 carbons? Cyclopropane. What do you think cycloethane would be? Cycloethane. And there's no cycloethane, so you need at least 3 carbons to be a ring, of course. What is this weird molecule that we've seen a couple times? It looks like a cyclohexane with some double bonds in it, but it's called benzene. And it is not a cycloalkane. So it's not a cycloalkane. Not a cycloalkane. It's something that we call aromatic. And this will be in chapter 15. ch3-ch4, which I think is organic too, actually. So we'll learn about that later. Okay? Alright, so cool. So we have some examples of simple cycloalkanes. Naming and properties. Naming and properties of these weird molecules. Naming first, we'll start with something easy, like what do you think it's called? It looks like it's a cyclopropane with something on it, right? A cyclopropane with something on it. What's the something that's on cyclopropane? It's a methyl group, right? That's a methyl group, so this is methyl cyclopropane. Methyl cyclopropane. Okay, what do you think this molecule is going to be called? It's something cyclobutane. Something cyclobutane. And the way we do this, we have to identify where those two things are, a methyl and a propyl, right? And we number the substituents around the ring. Number substituents around the ring. There's some rules to that we'll get to in a second, but we'll just arbitrarily, well, this 1 is where the substituents are, 2, 3, 4. Where you start numbering where those substituents are, and if you have multiple substituents, there's other rules, but we'll get to those in a second. So we number the substituents around the ring, and the name of this molecule then becomes 1-methyl, because both things are on number 1. 1-methyl, 1-propyl. Cyclopentane. Okay, so those are pretty easy examples, all right? Now, what if you have multiple substituents? Multiple substituents. So this is a little more complicated, but I'm going to give you some rules. All right. First, we're going to, and we'll practice this a little bit. First, we're going to create the lowest possible numbering system. We're going to create the lowest possible numbering system. I'll show you an example of this in a second. If there's a competition between a couple possible numbering systems, then we use then the lowest alphabetical substituent wins the competition. We'll see that in a second also. If there's a competition between a couple substituents, then we use the lowest alphabetically listed substituent. All right. So B is we number in direction of nearest to substituent. We number in the direction of the nearest substituent. Then we list our substituents. We list our substituents in alphabetical order. We list our substituents in alphabetical order. Okay? All right, so example. Is an easy one, and we have to determine a numbering system that accounts for these two substituents. Now there's two of them, one that begins in the letter B, one that begins in the letter M. So we're going to probably go from bromine to methyl. So it's going to be 1, 2. 1, 2, 3, 4, 5, 6. So we defined our numbering that way, and so the naming then becomes something cyclohexane, right? Something cyclohexane, and it's going to be 1 bromo, 2 methyl cyclohexane, 1 bromo, 2 methyl cyclohexane. We just use our alphabetization as the tiebreaker because there's two. You know, you could do 1 methyl 2 bromo, but that's going to violate the rule that we use the, you know, in a competition we use alphabetization to win the competition. Okay, let's do a more complicated one now. Alright, so how are we going to do this one? I have, if you have like 3 substituents like this, it's a little complicated. I like to use the sum to figure out the lowest possible numbering system. Okay, what does that mean? That sounds scary. So let me give an example with this one. All right. So the lowest possible numbering system. We have a couple ways we can possibly do this, and it's usually the way that's going to work. Alphabetization is not going to be the big thing here. We need to come up with a couple systems, and then we use the sum of the numbers to differentiate them. Let's show what I mean by that. I'm going to start with the bromine and say 1, 2, 3, 4. Okay. What is the sum of the numbers with substituents on them? It's like 1 plus 2 plus 4 is what? The sum of those 3 numbers, 1 plus 2 plus 4 is 7. Okay. Let's show a couple alternative numbering systems to show that they don't work, and the numbers are larger. This I'll tell you right now, this is the good one. All right. Okay, so what are some alternate numbering systems for this molecule? I'll draw them over here. Okay, so like this one. What if I number like from the bottom? Let's just number from the bottom. What do I get? 1, 2, 3, 4. Now, what's the sum of the 3 numbers with substituents? It's like 1 plus 3 plus 4 is what? 1 plus 3 plus 4 is 8. Bad. Okay, it's larger. It's a bigger number. Any other possible numbering systems? I don't know. Let's try, just for fun, let's do another one. BR. Okay. So let's go the other way from the bottom. Like we'll do 1, 2, 3, 4, 5. What's 1 plus 4 plus 5? 1 plus 4 plus 5 is 10. So these are bad. Okay, that's what I meant by rule number 1 up here, or rule number A. Create the lowest possible numbering system. That's the first thing you have to do. Create the lowest possible numbering system. In this molecule, either direction was the same, and that's why we used the bromine as the tiebreaker. But in this case, the lowest possible number kind of puts substituents kind of near each other, and that's why it's 1, 2, 3, 4, and that's why this wins. So we have the numbering system. How do we name this molecule now? Okay, so let's see. Maybe start with the end of the name. Cyclohexane. Cyclohexane, and we need to put things in alphabetical order using our normal rules. Where's the bromine on carbon 1? I like to do it this way sometimes, where I just list the things kind of vertically, the substituents vertically. I'm happy with you to do this on quizzes too. 1 bromo, and then it's 2,4-dimethyl. 2,4-dimethyl. Usually something like this. 1 bromo, 2,4-dimethyl, cyclohexane. You know, I'm happy with that as a name of this molecule. Alright, let's do another one. Bromine, chlorine, fluorine. Alright, so we have bromine, chlorine, fluorine on this one. So what's going to be our lowest possible numbering system? Based on what it has said, I recommend, if you see some substituents kind of grouped near each other, you should maybe start numbering, like maybe at the fluorine. So I think that's going to give us our lowest possible numbering system. So I think it's going to be 1, 2, 3, 4. What's the numbering? It looks like 1 plus 2 plus 4 is 3 plus 4 is 7, yeah? As opposed to, like, if I was numbered from the bromine, and you might think, oh, bromine is, lower in the alphabet, but that's not the rule. You only use alphabetization as a tiebreaker, I guess. This isn't a tiebreaker, right? So if we go 1, 2, 3, 4, well then its sum is 8, and that's bad. You want the lowest possible numbering system, okay? All right, so this is correct. How do we name it then? The left one's correct. How do we name it? It's going to be something cyclohexane, something cyclohexane, something cyclohexane, but the substituents are listed in alphabetical order. So it looks like it's going to be 4-bromo, 4-bromo, something chloro, 1-fluoro. Alright? So that's the end name. 4-bromo, 2-chloro, 1-fluoro. So even though we numbered from the fluorine upward for the lowest possible numbering system, we always list the substituents in alphabetical order using our crazy alphabetization rules that we learned earlier, right? BCF here. Okay. Alright, and another little thing about these cycloalkanes, substituted cycloalkanes. Substituted cycloalkanes can be stereoisomers. They can be stereoisomers, and that's what do we know a little bit about the concept of stereoisomerism. What's the basic concept of stereoisomerism? It's the three-dimensionality. The three-dimensionality. So we can say that for stereoisomers that the substituents can have same connectivity in a molecule, the same connectivity, but different three-dimensional arrangement. And that's what we mean by stereoisomerism. Stereoisomerism. Let's show an example. I'm going to show cyclopropane in this kind of representation where there's a CH2. It's kind of coming towards us. I'm sort of wedging it towards us, right? So we have the two distal CH2s, and then that CH2 is coming towards us. And I could imagine, like, on this back carbon, a CH3 going up, and an H going down, and maybe another CH3 going up, and an H going down. Alright. So, this molecule, what's the name, ignoring the stereoisomerism? It's something cyclopropane, right? And what's the numbering? It's 1,2-dimethyl cyclopropane. 1,2-dimethyl cannot spell today. Cyclopropane. 1,2-dimethylcyclopropane, right? But how would that compare to the similar molecule where one CH3 is going up and one CH3 is going down? It's kind of like one's going up, one's going down, right? Because the connectivity is the same, and if we give them names, the names are actually the same. So 1,2-dimethyl cyclopropane. You know, and I'm kind of showing, it's a little angled, I'm not really meaning anything there. So the big thing is 2 going up, 1 going up, 1 going down. So the relative orientation of the CH3s is different. I'm not trying to mean anything by that kind of angular arrangement as I drew it. But these are different molecules, and these are examples of stereoisomers. And they have names. The left one's going to be called cis. The right one's going to be called trans. 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 Cis refers to the 2 substituents going in the same direction. Trans means the 2 substituents are going in opposite directions. Alright? Cool. So, in this case, cis and trans are Latin. Cis for same side. Trans for across. Okay, so it's a Latin thing. Alright, cool. What about, I'll try to sneak them down at the bottom here. Another way to draw these kind of cycloalkanes is, here I'm showing the CH2 coming towards us, and then the substituents in the back going up and down. Another way I can do the same sort of thing is, and I'll do it right here, is say, well, that's a Br, this. Now it's a cyclobutane, right? A cyclobutane. And rather than the ring kind of coming towards us and away from us, I'm having the ring be in the plane of the paper. And now I'm having the substituents go either away from us, towards us or away from us, or like in this one, both towards us. Alright, so these are similar kind of idea. These are similar kind of idea. Here are the bromines coming towards us and the methyl's going away. Bromines coming towards us, methyl's also coming towards us. They're both going to be 1-bromo, 2-methyl cyclobutane. 1-bromo, 2-methyl cyclobutane. 1-bromo, 2-methyl cyclobutane. I'm going to draw the other one over here. 1-bromo, 2-methyl cyclobutane. Which one's cis, which one's trans? Well, the one where their opposite is trans. Trans. The one where they're together is cis. Alright, so we have trans 1-bromo 2-methyl cyclobutane, cis 1-bromo 2-methyl cyclobutane. Alright, cool. So that's kind of an introduction to stereoisomerism. I'll quickly give a definition of stereoisomers. Stereoisomer is the definition. Compound stereoisomers. Compounds that have same connectivity but different arrangement of substituents in space. That's basically the same definition I just gave, but that's fine. That is a nice little definition. Okay. I'm going to go back to the last ones I just did real quick. These ones. I just want to make it clear, and it should be clear to you now that you're more familiar with organic structures. Is like there's a hydrogen there and there, right? And they are going that, like, here the bromine's coming towards us. Where's the hydrogen going? It's going away, right? Here the CH3 is going away. Where's the extra hydrogen? It's coming towards us. Okay, so they have the same relationship, the hydrogens. We're just drawing just the substituents because that's often what we do. Here, the bromine and the CH3 are coming towards us, but there's also hydrogen there, and where are the hydrogens going? Well, they're going away. Okay, just be familiar with that idea with your structures. Yeah, when you're drawing and understanding these structures. Okay. Okay. So we gave a little definition of stereoisomerism. Versus, what's the other kind of isomers you know right now? Probably the most familiar with constitutional or structural isomers. These ones, the definition was compounds of the same molecular formula with different connectivity. Alright, so that's kind of the other kind of isomer that you know right now. Examples, if we consider like C5H12, C5H12, I think we did tell you this before, that, you know, if you have like CXH2X plus 2, like C5H12, that's what you get for linear and branched alkanes. So what's the easy way to draw C5H12? C5, it's 5 carbons, right? Pentane. But there's also, what are some constitutional or structural isomers? It would just be different branched versions of this. So rather than 5 carbons in a row, you might do 4 carbons and like put a methyl somewhere, right? So that's a structural isomer. Any other ones we could do? 5 carbons. How could you branch 5 carbons in some alternate way? Well, maybe like that. That's another constitutional or structural isomer. C6H14. Is that, and remember also, if you have like CXH2X, like CXH2X, that is usually the formula for like cyclic alkane, like chapter 4, right? Or also if you have alkene, like a double bond. But this is also CXH2X plus 2, right? CXH2X plus 2. 6 times 2 is 12, add 2, you get 14. So how do we draw some of these guys? Well, start with the easy one. 6 carbons. 1, 2, 3, 4, 5, 6. Then you could start doing some branched ones, right? Let's see, did I do that right? 1, 2, 3, 4, 5, 6, yeah. Yep. Any others? You could probably come up with some alternate branched forms of C6H14. Like maybe, how about 2 carbons and then 2 methyls on each? That would work. You could also do, let's see, 5 carbons. 5 carbons with a methyl right there. I think I'm doing one, there's one more I could do that I usually just start with a simple branching and then I move to the more complicated branching. So maybe one more where I have 5 carbons, and kind of like this for this last one, but maybe I'll just put the branching like right there. Alright? Each of these, you should be able to name all of these. These are all very simple naming, right? So 2-methyl butane, that's 2,2-dimethyl propane. This is 1, 2, 3, 4, 2,2-dimethyl butane, 2,3-dimethyl butane, 3-methyl pentane, 2-methyl pentane, etc. Right? Okay. So what happens if we do like C5H10? What happens if we do like C5H10? So remember, for acyclic it's like CXH 2x plus 2. CXH 2x plus 2. What if you have CXH2x? These are not simple alkanes. And this would be a typical formula of like a cycloalkane. Yeah. So what's a simple one to draw? 5 carbons. Cyclic 5 carbons. What is that? Maybe it could be cyclopentane, right? So what are some of the variations we could do then? Additional structural isomers of cyclopentane. What do you think? Cyclopentane. I could maybe do methyl cyclobutane. Methyl cyclobutane, right? What else could I do? So that's like, you know, instead of 5 carbons, I could do 4 and an extra methyl. What other ones could I do? Maybe I could do 3 and then have, what? An ethyl. Maybe I could do 3 and instead of 2 carbons as an ethyl, I could have 2 carbons like that. Or maybe I could have 3 with, instead of 2 carbons on the same carbon, maybe like that. You can kind of keep going with this, right, and draw some different structural isomers, right? Okay. What's another way to do it? I said that if you have CXH2X, you can either account for it with cyclic alkanes. I think I drew every possibility, right? There are like cis and trans isomers of this, but that's not what structural isomers care about. They care more about the connectivity, not the three-dimensionality. But I did say that CXH2X, another way to do it is by having alkenes, right? Like a double bond. So, right? So, as an example, is that 1, 2, 3, 4, 5? I messed up. If you add a double bond, you also get a CXH2X. Let's count the hydrogens. It's 3, 4, 5, 6, 7, 8, 9, 10. You can see there's 10 right there, right? Whereas like if I do like C5H12, that's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how we get that. Anyway, so that's another way to account for like a reduced number of hydrogens between like these top guys and this the bottom one. All right. Okay, next thing about cycloalkanes as we proceed through chapter 4. Next thing to know about cycloalkanes. We're on to number 2. Ring strain of cycloalkanes. Alright, so So the basic summary here is that some cycloalkanes are more strained or unhappy than others. Small rings in particular strain the Sp3 geometry. Small rings strain the Sp3 geometry. Okay, so what is the normal Sp3 geometry? Like, what's the normal bond angle for Sp3? Like methane or something? What do you think? What's the normal bond angle? Is roughly 109.5. So the normal bond angle is 109.5. And so if you just think about, like, let's draw it bigger. Cyclopropane, for example, do you think it can achieve 109.5 degrees? And I mean, if you look at the angle, just kind of superficially, that does not look like 109.5 degrees, right? It looks more like, what, like 60? Do you think that's happy? That we're bending the molecule? And it's this is definitely not very happy. If we look at cyclobutane, I mean, in this kind of representation, it doesn't. It will pucker and change its structure a little bit, yeah, it looks 90 degrees, right? Now it's going to change a little bit, but overall these are really unhappy. 60 and 90, very unhappy. What about Cyclopentane? It turns out that this is roughly about 104 degrees, which is not as bad. You can understand that, right? That 104 is a lot closer to like 109 than like 90 or 60. Okay, so anyway, so we'll just say not as bad. Keep that in the back of your mind. That cyclopentane is actually a reasonably stable, happy structure. Okay. Alright, so we're going to do one last little thing here. So we're going to quantify the concept of ring strain, and then we'll use that in a really cool calculation next time. But I just got to show this one thing. Alright, so ring strain is observed by heat of combustion. Heat of combustion. What do you think heat of combustion means? It's essentially, as you might be able to surmise, heat of combustion just means you burn something and then get some heat out, right? You burn things, and certainly organic molecules, when you burn them, they release heat. And so we're measuring the heat of combustion. We call that delta H under standard conditions combustion. So this is our kind of the normalized heat of combustion. Okay, so what we're going to do, and I'll start this now and then continue next time, is we're going to compare cyclic versus non-cyclic. Alkanes. We're going to compare cyclic versus non-cyclic alkanes. I'll give you a hint. Non-cyclic alkanes are not strained, right? Mostly. In terms of the serious strain we encounter up here, this is a very serious strain due to bond angle deviations, right? Okay, so what we're going to do is we're going to compare cyclic versus non-cyclic molecules, and the trick is that non-cyclic molecules are not strained, right? If we think about like ethane, propane, butane, pentane, those don't have any kind of ring strain because they're not rings, right? So, but you can burn them, right? We know we can burn alkanes, and they're used as natural gases. That's how we heat our homes and stuff, right? Alright, so we're going to compare cyclic versus non-cyclic alkanes. But the thing we need to do first, and this will be just take a second or two, we're going to look at the heat of combustion for a series of alkanes. And we're going to try to figure out, like, how much heat do you get if you just burn a CH2 from a molecule, if that makes any sense. So let's think about propane. Of course, propane is this, and if we burn it, we get negative 530.6. These are all kilocalories per mole. We get negative 530.6 kilocalories per mole. And if we burn butane, how many carbons are in butane? Should be 4, right? We get negative 687.4. So that just shows, of course, you burn these molecules to get heat. That's why we use them as fuels, right? The difference will be important. It's roughly negative 156.8. Negative 156.8 kilocalories per mole. Alright, so these are all kilocalories per mole. Okay, and if we do pentane, how many carbons are in pentane? It's 1, 2, 3, 4, 5. It's about negative 845.2. So it seems like every time you add a CH2, you know, and just like there's energy in these bonds, right? You burn it, energy gets produced. And we do the difference between like these two carbons. The difference is, so up here I'm showing the first two, here I'm showing the second two. It's about almost the same. It's negative 157.8. Okay. And now imagine we just do a whole bunch of these. Just go, you know, we do like a whole series of these alkanes. So when averaged over more, when averaged over others, we'll say. Delta H combustion is negative 157.4 kilocalories per mole. Okay, so this is kind of where we're ending now. And so over a large series of alkanes, if you average them, you get basically 157.4 kilocalories per mole. And that is just kind of like a defined value for per CH2. Per CH2. I'm going to write that down there. Per CH2. Let's do that a little more prominently. Write that really big. Negative 157.4 kilocalories per mole per CH2. Okay? Okay, so for these molecules, which are all unstrained, they're not strained, right? When you burn them, you're essentially getting, on average, 157.4 kilocalories per mole per CH2. That's going to be useful when we go back to the cyclic ones that have strain in them, because they all have CH2s, but we can actually kind of differentiate the bond angle strain from the strain, from the energy you get just from each of the CH2s. So what we're going to do next time is, given this number, which tells you, how much energy is in each CH2 in an unstrained molecule like ethane, butane, pentane, and all, this average goes up to like 10 carbons long. What we can do is really figure out how much additional energy is in certain CH2s, like these strained ones, right? These strained ones have extra energy, and all we have to do is determine basically the difference of like burning these molecules versus burning these molecules, and just normalize this out based on the number of CH2s. So we'll do that very nicely. For now, just you know, have this number in your notes, and it'll and we'll use it next time when we discuss the individual strain in these highly strained cycloalkanes like cyclopropane and cyclobutane. All right, see ya.